Okay, so this talk will be about a system that we call Cocos AI, an open source system for secure multi-party computation with ease. So let me present first the speakers. So my name is Drasko Draskovic. I'm CEO of Abstract Machines, which is a startup involved in security from Paris. And then there is Dusan, who will be doing a short demo. He's the CTO of Ultraviolet, a company located in Serbia that is especially focused on secure multi-party computation with confidential computing, but also with LLM inference protection, which seems to be very, I would say, popular these days, and then confidential containers, and recently started working also on implementing a keystone inside the RISC-V TPU, something that seems to be interesting, as only NVIDIA currently has a TEs built in. So what I want especially to mention is that most of these, let's say, insights that I will be presenting today came out of a large-scale EU research projects in which both Abstract Machines and Ultraviolet are involved. One of them is, for example, confidential 6G, which is aiming to build a confidential computing into the future 6G networks. So all of those projects are large-scale projects with 5 to 7 million of budget for each of the projects. So you can imagine the scale of those. Another one is Titan European Open Science Cloud. So it's an academia cloud in which various European institutions exchange data, and so the idea is to protect data using confidential computing. And then one very interesting project started recently called Elastic, in which even Mike is involved as an advisor to bring a huge experience in WASM especially, and we are here researching the application of confidential computing coupled with serverless and fast in a lightweight manner, and this is where also the idea of using WebAssembly came into picture. So the research is then poured into an open source project that we call Cocos. We called it Cocos AI, so confidential computing system for AI. But then also there is a part that is called Prism AI that is more kind of user interface, which is, let's say, less important than the core that is presented here. So just for reference, it's Ultraviolet RS / Cocos for those who are interested. So what are we trying to solve, and what we are researching through those projects with all the other companies and consortiums that are involved is a way so that different organizations can securely exchange data without a single kind of source of trust or a single organization that can actually coordinate or be an owner and see the data or see the algorithm itself. So that's a bit trickier case than a single party confidential computing, where an owner of the computation would typically create and prepare the secure virtual machine, confidential virtual machine, and then deploy into it algorithm and data, and obviously that would be hidden from the, let's say, cloud provider or internal threats, but then it would be visible to those who created the virtual machine. Here, the idea is really how to prevent everybody to get into the virtual machine, to the enclave, but nevertheless be capable of sending data into the VM and sending the algorithm, and then orchestrating the execution of this algorithm within a secure enclave and retrieving the result. So the features that were missing practically from what was provided by the existing tooling and offerings from CSPs are some parts that are more, let's say, traditional web development. Okay, this is something that was easily done, but then the orchestration of this computation was done through the in-enclave agent, which is part of the Cocos system and presented in open source form. But more importantly, there was a need for this hardware abstraction layer, which is a small embedded Linux OS that we built through the build root system, and then set it up in such a way that we can execute all the measurements in different phases during the secure boot, meaning from the OVMF through the U-boot bootloader, then Linux kernel itself, and finally rootfs, where we used initially init ramfs so that we keep everything in RAM where it is encrypted, and prevent even swapping to disk, and ensure that practically everything is in the secure enclave. So one big challenge was building that hardware abstraction layer in a proper manner. Then another challenge was building this in-enclave agent that would coordinate and schedule the execution of the algorithm over the combined data sets, and while keeping this traffic encrypted. And then, of course, this in-enclave agent should be capable of doing the attestation measurements within the enclave itself, because nobody can enter the enclave. So we count on this agent to do a lot of things. And then we needed the tools to communicate with this agent and do the actual attestation. In this particular case, we opted for attested TLS, meaning that on the establishment of the communication, the CLI and the client that should upload the data, and you will see this in a demo, does the verification of the attestation, and then and only then establish the TLS connection which can be used. Just as a small side note, the IETF RATS group specifies the attestation procedures, as you know, but one thing that we didn't build in initially was in handshake measurement. So it was not needed for our particular case, but now we are fixing that, and there will be another pull request coming very soon that fixes this as well. So let me go very fast through this slide.
Could you just explain what you mean by in-handshake measurement?
So it means that when you start a TLS handshake, it's actually then when the agent inside the enclave will redo the measurement to have the most update measurement, and then send this. What we did in the beginning is that the agent would on the boot do the measurement and have it and send it every time when it's requested. So in our particular case, as I said, because we cannot change nobody cannot change the contents of the enclave, we are sure that it will stay the same and that the integrity will be kept. But just for the purpose of following very strictly the IETF RATS recommendations, we said, okay, it's not a problem, let's do it in a handshake, and as we publish everything open source, this also is kind of a blueprint for others to reuse the code. So this is mostly why we are doing it. So the idea of doing this multi-party computation is that there is somebody who creates the computation as an entity, kind of metadata, describes what the computation is, etc. Then starts the computation. Once it starts the computation, the enclave is created dynamically by something that we call VM Manager. So the appropriate confidential virtual machine is spawned, and then inside all this, I mean, there is an agent that is getting booted, and then it can accept those data sets and algorithms that are coming from different parties. Nobody cannot SSH into the enclave or do anything else. They can only send the data. The attestation is done automatically through the TLS establishment. Once the data is sent, the agent is intelligent enough, because it owns the computation manifest, to understand when all the data sets are present and the algorithm is present, so it can immediately move into state machine, into running phase, then run the algorithm. And once the results are ready, then the result consumer can actually pick up those results, and of course only the result consumer. So there is a governance built in with all the policies that are needed. So maybe, yes.
Or later,
maybe better later because of those strict timings. But so just and maybe it will be answered during the talk. So the architecture also can give you some hints of how it is structured and how it works. Actually, there on the left-hand side is a cloud where I would say this is traditional web part and nothing especially interesting here. We borrowed a lot of blocks from the one open source project called Magistrala that is dealing with the Internet of Things and in general, I would say the organization and management of the web components that are needed for messaging and user interactions and thing interactions, which in our case is computation entity. But the right-hand side is interesting, and it's actually, those are the components that we had to build. So the manager that is provisioning the VMs in a proper manner, in our case, interacting directly with the hypervisor, but sending the correct parameters and the correct UEFI or OVMF block, and we needed to build this one from Tiago Core open source UEFI. This is also what AMD is doing and suggesting, so that you can actually get those stamps and hashes and put them into the measurement when the CVM is booted. So this is why all this work has been done, in order for us to produce the correct attestation in the end, and not to have some kind of attestation service that you should trust. And in this particular case, what is tricky is that nobody trusts nobody, but we need to produce a valid CVM, and inside of it, now because it's a bare metal machine, we needed to produce all the environment, so the operating system, very lightweight, the one that has been hardened through the build route and configurations, and that has a appropriate environment, but not only environment, but also this manifest that comes from the left-hand side when the computation is started. So the manifest travels into the trusted execution environment through, in this particular case, through a vSocket, so virtual socket between this manager and the VM. And then the agent is spawned, and the agent is now accepting those connections, TLS connections, according to the manifest. The VM is monitored through a vSocket, a virtual socket, by the manager, who then propagates the data information to the management, and you can pick them up via API, so that actually you understand what is happening with this VM. I'm just pasting here the UI so that you can also have hints of how it works. So in this simple UI you can create various, of course, users and groups, and that would represent the workspaces that would represent a consortium kind of workaround. And then users can define what we call computations, and the computations are, you define who is a data provider, who is a algorithm provider, who is a result consumer, and practically set the kind of governance information on the computation. You tell it, of course, what are the data sets, what are the hashes of these data sets, so that they can be verified inside the enclave, and you also produce a certain certificate, so that TLS connection can be established. I forgot to say that clients that are uploading the data and the algorithms are actually using mutual TLS, so that both the agent and the agent has a public keys of each of the clients, so that mutual TLS as a, let's say, strongest form of TLS can be established. Then there is something that we call backends, and that the idea here is that you can have multiple managers. Is that kind of, if you run this thing in the public cloud, which is this part on the left-hand side, so very traditional web part, you can run it anywhere. You don't care about this, but you can bring your own kind of backend, bring your own SCV, SMP machine, or bring your own Intel TDX machine or whatever, so you can connect your data center, your local data center, or whatever your public TE to this system in the cloud, and then you can send your computation to a different kind of backends. So it's so the idea is that you can have a backend that come from different architectures, from different data centers, from even from public clouds and so on, but that you can use the same system to define what the actual computation is, who are participants, and so on. So I mentioned the manager, so those VMs are created dynamically per computation run. You create one very lightweight VM because we build our own kernel. It is extremely lightweight, around 8 megs in size. RAM is a little bit, init RAMFS is or RAMFS is a bit larger, but basically it boots in a matter of seconds. And then it is ready to accept the connections from different clients. Here is the idea is that the cloud part, you can run it in Kubernetes and then scale it, and then just various instances can send commands for the various computations to be deployed. Inside each of the enclaves, you will have agent, as I mentioned, and it is the one that can read the computation manifest and decide practically will it accept the connection from the data providers or algorithm providers, and will it give a connection or a result to the result consumer. So it's a state machine that can understand by reading the manifest how many data sets are involved in this computation, that can accept the data set that has been uploaded, that can verify the hash of this data set, that can do a lot of checks of this type, and then once everything is ready, can actually the sub-process can actually start the computation, and then monitor it until it's done, then notify the completion, and then the result consumer would come and pick the result at some point. Again, only agent is inside this enclave, and nobody else can enter it or change anything inside of it. So about the remote attestations, I mentioned that the agent itself is in charge of doing the measurement, and we are doing this through the guest attestations. So this is a procedure that is, I would say, known today, and the only, I would say, particular thing is that we built the validation of the measurement, the attestation inside the CLI, which we use also to upload the data, so that on the TLS establishment, that's why we call it attested TLS, on the establishment of TLS, we are doing automatically the verification, and then and only then the connection is established, mutual TLS connection is established, and then data is uploaded. So it's kind of even transparent to the user that everything is, going according to the plan and easy to use, let's say. What's interesting is that we succeeded to build into this embedded Linux that we are deploying different runtimes. So you can, of course, the first target was a Python runtime with PyTorch and similar, so that we can run AI workloads. Then we try to, look at more lightweight approaches to AI algorithms. One very interesting library which we played is written in Rust called Burn, kind of PyTorch competitor, but compiled and more lightweight. And then we opted for, binary, ELF binary executions. We looked more at the isolation of the execution itself, so how can we prevent this process to do something, let's say communicate over the network and so on. This is where the deployment in Docker inside this confidential VM makes sense, also because of the environment that you might bring as an algorithm provider. So if you have other dependencies or libraries or something like that we don't provide already in this very lightweight operating system, inside the enclave, then probably you can upload the Docker with everything inside. And that was an approach also that is enabled today. And finally, WebAssembly, there is a WebAssembly runtime inside that we built in, and so you can run a various WASM workloads as well. So we covered those, and it seems to be kind of very extensive and covers a lot of use cases. So what I would like now is that Dusan shows us a short demo of how it works, mostly in this user interface, and then on one Dell machine that we have in our data center. It's ARM EPIC 3, AMD EPIC 3 SEV SMP machine. I don't know for the questions, maybe we can leave it later, the one that you had. Okay. Yeah. So maybe Dusan, go ahead then, please.
Thank you.
We have 10, 15 more minutes.
I'll just go back to the architecture so that I can maybe switch back in between the architecture and the demo. And this is the UI. Maybe the session expired now, maybe not. No? Okay. So this is the UI Drasko presented. This is the live demo, so if something goes south, I will just pretend everything is okay. So yeah, this is, I will not talk a lot about what's going on in the cloud part, that is on the left-hand side here, because these are components that are not necessarily related to confidential computing, even though there are some authorization and policies and user management and workspaces, invitations, different user roles and so on that you can do different types of things here, but what is important here are backends and computations. So here I have one computation. We have a lot of computations. This is the workspace we are sharing with our colleagues that are testing it. So here we have one computation that is fraud detection algorithm. Is really not important which algorithm it is, but for the purpose of demo, we wanted something that is fairly short. So that we can show it live. And as you can see here, the computation actually represents the metadata about the workload that is going to happen inside trusted execution environments. So this workload includes some algorithm data sets and obviously the result consumer. And this is the collaborative platform. And in that sense, data sets, providers, and algorithm and result consumer are usually not a single person. In this demo, I put myself just so we can more easily go through it. But in general, it's usually at least two persons because data sets and algorithm providers are usually not the same. Result consumer can be one of those, depending on the use case. But here, this is only single person. When I created this computation, I have uploaded I used our CLI tool and uploaded my public key so that I can use my private key to establish a mutual TLS. And then I established this mutual TLS with this particular agent address. This agent address is actually related to the backends that Drasko has mentioned, and these backends, this is actually the real physical machine in our private data center, and this is the pluggable part that Drasko mentioned earlier, where you can actually bring your own data center, bring your own machines for as long as it's set up correctly, and you can use different types of backends, even cloud, for as long as it does support TEs. You have to generate certificate, and then the operator needs to upload that certificate and start the agent component, this one, the manager component on the bare metal machine in order for everything to work, because we are going to talk to this manager to practically spawn this trusted execution environment with our minimal operating system and agent running in it. But you can do that. So I'm going to go back to the computation.
Maybe what would be interesting is to show the backend information.
Oh yeah, I'll do that. Let me just run the computation. So we will receive here you will receive soon, as soon as the computation virtual machine is ready, we'll receive the port to which we can attach. That port is actually the port of the this agent running in TE, and from that point on, we are going to use our CLI to communicate directly to the agent. So directly to the agent in trusted in enclave agent, rather than talking to the cloud or any in-between step. So I have received the port, and I will show you quickly. I think, yeah, it's the same port. Okay, so I will now, since the VM is provisioned correctly, I will now upload the algorithm. Here we are talking about Python, and you see that it is now waiting for data to be received. I'll now upload the data as well. So these are, since this is fraud detection, I'm uploading some. This is all mutual TLS, so this data is encrypted in transit and also encrypted in use because this is going to TE. I'm uploading now this data. Ideally, this would be the different user uploading from their machine, and the computation is now started, or rather, it is running. You can see here logs. Logs are going through agent and this manager component to the cloud, to this what we call the backend service, and then we show it on the UI. And here on the backend, you can see some data. This is not the full data about the backend information about so here, what is missing actually here is measurement. I will not show you the actual attestation now because I'm missing some of the OVMF. I'm missing in particular OVMF and the Linux kernel that I need to calculate measurement on my side. But we have that part included in this tool. So in the future, the plan is to use that to establish a tested TLS so that all of these steps that I'm now taking are actually involving the attestation procedure in itself. We already actually support the better part of it. As Drasko mentioned, we just recently changed some things. Namely, we now are doing the attestation every time we are calculating the measurement every time we establish the connection, but currently I will not show it in this demo. And let me see if the computation is done. I mean, there is nothing. It is still running. As soon as the results are ready, I will be able to fetch results like this. Yep. So it's still not ready. And when it's ready, the computation will wait for the user to terminate it, and that will be it. So the result will be this. Since the result is a model for, I don't know, AI model for this fraud detection that you can later use. It is, I think, JSON binary object or something like that. So yeah, this is the demo.
Maybe if I can add, as you saw, in this particular case, we are doing the training, so it might take some time, and the result would be model. But you can also do the inference without any problems. You can use it also for a single party kind of execution, no problem there. So you can have the same user that is at the same time data provider and algorithm provider. So there is a modularity to the flexibility of how you can use it. And we created a whole bunch of examples and in an open source repository under Ultraviolet RS/AI, where we given more complicated AI training models for COVID detection, for fraud detection, for turbofan jet engines and predictive maintenance and so on, and tested them all through the system, and also in various forms, in Docker containers, in WASM, through WASM images and so on. So this has been the work that has been done already and published inside the repository.
Also, yeah, results are ready. Now, we'll pick up the results and that's it. But you see here in the CLI, you can specify which type of, so here we are using Python, but you can specify also Docker, WASM, or executable. Then we are sending the actual file. Ideally, I mean, in the real world scenario, Docker is probably the most convenient way to do it because of the dependencies. The exe file may or may not work. If it's statically compiled, it will work. If it's not, it depends because we have very minimal Linux inside of it, so there may be things missing. And then we also have specified this requirements file so that you don't have to pack Python or anything to it, and then we can go to
so
results.
Because
and then we retrieve the results. Yeah. And results
this can conclude the demo, Dusan, I think, and we can leave 5 minutes for questions if there are some. Yes, let's start with
Repeat the
you.
questions back, yeah?
Okay, yes, I will.
Okay. Can you explain what you mean by attested TLS? Is this the RATLS from Intel, or is it the ATLS, ITF draft, or is it something else?
So the question was, what do we consider under attested TLS? Is it something specific from Intel or ITF draft or something else? It is ITF draft that we are following. And we are involved also, I mean, through those European projects, there are people who are very involved in ITF groups and working, especially in RATS, working and following what is happening there. And so we try to follow especially the spec of ITF for the in-handshake attestation measurement, as I mentioned, and the attested TLS is happening during the handshake where the client that is establishing mutual TLS with the agent that is running in the enclave is actually doing also the verification of the attestation report that has been received, and only if this report has been valid, then it proceeds with finishing the handshake, TLS handshake. So it's attestation that is built into the connection establishment, if you want.
And we have implemented those extensions that are, we have also implemented those TLS extensions that are specified by the standard.
Yeah.
We wrote the
Great.
So yeah, I'm also curious, following on, you say you've implemented it, what is the TLS stack that you're using?
Yeah, so we use the agent is written in Go programming language, so everything is more or less written in Go programming language, but we were missing the extensions in Go because Go programming language mysteriously do not support those, you can say better. So we had to use OpenTLS, so the C stack, and then do the foreign function invocation on those.
Sorry, no, it was just a suggestion.
There is just 5 minutes maybe of budget.
Let's continue. Yeah.
I was wondering, because you have that combination of Kubernetes and on-prem, are you familiar with the confidential container project, which also from a naming perspective has some similarity and it has a different...
Yes, so the approach as well, and we are working on this and examining, especially the idea of agent that is running inside the container. So in case of confidential containers, it's Kata container. Also, they are using, what is very interesting for us in the future also is building a Docker registry that from which we can pull the Dockers and the WASM images as well, so that you don't have individually to upload, as Dusan showed, the data sets, like different parties can upload and encrypt their containers into a registry, and then it can be pulled. But it's a little bit trickier to deploy locally than for everybody, because everybody would have to have local Docker registry then as well. Sometimes it's easier to just have a CLI to upload. It depends, but the approach is similar, and we are working on this, especially through those European projects on enablement.
And
I mean, the reality being deferred, that's also part of that.
Thanks. So maybe just one more question.
So in the case of multi-node, right? Let's say if you want to multi-node AI, where the GPUs on two different keys have to talk to each other to exchange gradients or whatever, what is the confidentiality that you guys provide on that? Like, is it IPsec, TLS, or how?
So the question was about the multi-node execution of the AI. So currently we were working only on single nodes, and we are working on enablement of NVIDIA GPU connected, the H100, or the only one that has TEs on the market. As I mentioned, that was a pain point for us, as we are really with open source mindset, and this is why we started researching RISC-V based TPUs that can be, in which we can build a keystone. One of the projects from CCC that was mentioned, a RISC-V TE built into the FPGA that we want to promote and make it like very useful and even competitive in the sense of security, because no other, to my knowledge, has this solution, like no other company.
Thank you. I'm going to finish it there, I'm afraid, Osama, because they've had extra time because I finished early, so I want to give James some of that ahead. So, thank you very much, gentlemen.
Thanks. Thank you.